Okay, so I will announce the next speaker, who is M Dernjatin. He's a curator from Sea Life in Helsinki, and he will talk to us by speak downscaling denitrification. And he announced to make the presentation in Finnish, but I'm not sure whether he dares.
Hello everyone. I had a quick chat with Jan Möller during the break, and he expressed his worry for me doing the same talk every time. But I think I haven't done this before. Okay, so this is very straightforward, down-to-earth presentation. It's actually of my colleague's home tank, but it could be any display in any Sea Life Center or any of your institutions. One standalone tank with a nitrate problem. Well, this one shows you some lethal concentration values of NO3. As you can see, they are fairly high. For example, minnows and salmons can cope up to 6 grams per liter. That's the dose that kills them in a certain time. But if you look at the values of Chinook salmon or rainbow trout, it's in the scale we usually have in our tanks. It's around 10 to 30. That is lethal for larvae. So that gives you an idea that nitrate is a problem. These are all fish, of course, but invertebrates are even more sensitive. Well, the process itself is in routine use already in our institutions. It's either heterotrophic systems or sulfur-based autotrophic reactors. So we are well familiar with these, and we know that they do work. This one is the one we have in Helsinki. There's actually 2 different units, and they are treating 2 systems, research systems. One is 350 cubic meters. And it's been in use for about 6-7 years soon, and it's been very stable. We have low nitrate levels, around 30-40 constantly, and it's quite easy to maintain and operate. So that's quite nice equipment there. And we can see clear results. We do less water changes now. It's about 10-20% saving in salt cost. Water quality has improved. Nitrate is low, pH is better now, and well, there is clearly reduced mortality. So this is all in main recirculation system, but after installing this thing, we've been able to put invertebrates and jellyfish and everything in this same system, which is one big benefit, of course. Well, there's not many such things in smaller tanks at the moment. Our live coral displays mostly rely on, well, water changes and gravel maintenance. There's some natural denitrification in live rocks and sand beds, but it's spatial and temporal, and it doesn't always go that way. You can see nitrate builds up in our reef tanks easily. But in general, these values between 10 and 20 seem to be negative for the live coral displays. This picture is from Helsinki. It's an old picture already, so it's now overgrown with corals. The only time we noticed bad growth was when nitrate went above 50 milligrams, and then we increased the water change rate, and the coral started to grow again. So it was probably NO3 that caused the problem. Well, this case is quite large home tank. It's about 4 cubic meters. the actual tank, set up 2006, originally for fish-only display. And there's quite a lot of livestock in it, actually, a bit too much. A lot of food goes in. And it was fine after setup and the algae periods and everything, but after a couple of years, problems appeared. Well, it was supposed to be a fish-only tank, but surprise, surprise, more and more invertebrates went in, and then at some point they started to die. And water changes were regular and quite large, actually, almost 40% monthly. If you look at the water quality during those days, it seems to be okay, except nitrate levels are quite high. But there's no other clear reason in these parameters that would explain that almost all corals died. So we thought this is a nice project, and we kind of scaled down our own unit from Helsinki Sea Life. There's no formula, it was done with the feel of thumb. But we assumed that 1 kilo of fluidized sand in the reactor could treat roughly 1 cubic meter of water. That was just estimation. And of course this guy was happy to have another fancy equipment to play with, like all hobbyists are. This is how it looks like. It's a very simple acrylic pipe, 1.5 high. It's 160 mil pipe because it happened to be the pipe we had as a surplus available. And there's 5 kilos of sand, which is fluidized, of course. And it can take roughly 10 liters per hour and still remain anaerobic, and the process still remains as it's supposed to be. For carbon source, we choose ethanol. In Helsinki, we use methanol, it's fine as well. We'd like to use ethanol, but they don't give us ethanol. They don't even give us denaturated ethanol. Strange. So this is how it looks like. It looks a bit like protein skimmer, actually. We built this cup up there to collect the foam, which we assumed will build up, like it does in our system. There's a stopper that prevents foam going back to the reservoir. There's a drain to waste so that this collection cup can be cleaned easily. And then there's 5 kilos of sand and internal circulation, of course, to keep it anaerobic, with a 3-phase pump, frequency controlled. The pump, if electricity goes off for some reason, and when it comes back, the pump pumps 10 seconds with full force, and then it slows down so that it will push the sand up before it settles. The reactor chamber is 22 liters, and there's a redox bypass loop in the pressure side of the pump, a non-return valve to keep most of the sand out from the impeller housing. So it's quite simple. Well, we purchased this fancy device to do some measurements. We were lucky to have such thing so that we can get accurate readings. We mostly use it for NO2 and NO3 in this case. Didn't much need to do anything else. And this one is very reliable. We use same in Helsinki, and it's a bit expensive, but if you compare results this week, last week, a year before, you can see that they stay within acceptable range. You don't get 200 milligrams nitrate today and 50 tomorrow. It's if used correct way, it's reliable. Well, we were able to steal some sand from Sea Life. It was, of course, pre-maturated, We replaced it with fresh sand, so we didn't see any change in the actual filter after this operation. And then the sand was kept in a bucket in a garage for 10 days roughly, because there was some delays, but it didn't matter at all. So we put it in the reactor and put the reactor on, and it was doing its job within 2-3 hours after this. Unlike most of the aerobic filters, which we try to pre-maturate somewhere and then we move those to another system and nothing happens for 2 months. Well, redox is very important because we use it to control the carbon dose, ethanol dosing into this device. And it's best located in the pressure side of the fluidizing pump in a separate bypass. What is interesting, if you put the probe elsewhere, you get completely different readings. There's actually 2 redox units in this device. The other one, which is controlling the carbon dosing, is showing similar values as we have in sea life, but the other one, which is located in the suction side of the pump, is showing completely different values. And if you swap the probes, it's still the same. So it is important to know that, and it's best to set those set points for your carbon dosing based on what is the effluent nitrate level actually. And then you can set it to a right level. We use set point 170, 180 millivolts to switch off. These are minus. Sorry, there should be minus in front. To switch off the dosing pump and to stop the denitrification process. And then once the redox is rising again, the dosing pump goes back on, of course. And the fluctuation is quite small. It's plus minus 10 to 15 millivolts. So after the pump goes off, the redox falls maybe down to minus 190 millivolts. Then it starts to rise again. And at the set point, the pump goes back on, and soon after it starts to fall again. So the foam collector, we consider that's a very important thing to prevent all this sludge, the bacterial biomass, getting into the tank, but actually there has been no foam at all in this unit during these years. So that was quite nice to know this. So if it's operated in low nitrate conditions, there's not much foam coming out. Also, we use different carbon source, but it shouldn't really affect so much. So this is the carbon source. 3 bottles per year is quite enough, so it's not very expensive. You can use pure ethanol, of course, or methanol, or vinegar, acetic acid, basically sugar. That would probably cause problems, but it doesn't really matter what the carbon source is. And like I said, the location of this carbon feed affects redox value very much. We don't know why, but something happens in those pipes in very short distance that gives so strange differences in these values. But some people pour vodka straight into their reef tanks. I don't think that's a good idea, actually. It probably seldom finds its way to where it should be. The carbon is needed. But it definitely benefits all other bacteria in tanks, so you end up having cloudy water soon. So what happened? This was interesting in the reservoir in which the reactor is connected. We had a massive outbreak of sponges. So whatever comes out from the reactor, probably bacteria and ethanol and stuff, benefits these guys a lot. So they covered all surface in a few months' time. And of course, since there's sand in the reservoir, probably some denitrification happens there as well if excess carbon leaks out from the reservoir, from the filter. Unfortunately, there's no pictures of this display from that time when it was in bad shape because this guy doesn't have a camera. It's probably too expensive. But there's no visible cloudiness in this size display. Even if you look through the small window along the whole tank, you can't really see any difference because of this denitrification filter. Nitrate level, which was around 50 at some point, settled down to well below 10 in 3 months. And it has been there ever since, so it's a very easy and stable process. We didn't see any increase in NO2 values, and the pH has stabilized. It's not going below 8 anymore. It used to be below 8, especially in the morning, right before the lights go on, so that's definitely big benefit for all these animals. And there's 50% less water change now, or even more actually. So fluidized bed, when it's fluidized, it's self-cleaning, it's almost maintenance-free, and if it's controlled with redox, it's an easy device to operate. The only problem is all these dosing pumps cost quite a lot, and this circulation pump, which is three-phase pump, they are quite expensive. So this device costs about 3,000–4,000 euros. So it's not very cheap. But on the other hand, what's inside the tank is very valuable livestock. So, but it pays back in terms of reduced salt consumption, of course, and reduced mortalities. So finally, we can see some coral growth. These have been growing now roughly 1 year, so it's picking up, and after a couple of years, tank is probably very nice. That's about it.
So thanks a lot, Markus, for this very practical and hands-on presentation. Are there any questions? We would have some time. There are, yes. Max?
Did you try to work at lower
You're getting the microphone.
Did you try to work at even lower levels of nitrates?
No, this is the lowest we've tried. It's around 7. It has been around 7 almost 2 years now, and it's stable.
Okay,
The process is very stable. We've been worried what happens when nitrate goes very, very low, but at least in this case it seemed to work. And the redox values, the set points can still be the same, so there's no need to change those.
Okay, Daniel?
Did you at the same time look for the phosphate level?
No, unfortunately phosphate was not measured, and that's of course a big worry what happens now when the water change rate has been reduced so much. So that's an important thing to find out. But these do not really affect phosphate. It said that fluidized bed would reduce phosphate levels because of this excess biomass, this sludge, this foam that comes out. Of course, there's lots of bacteria which store phosphates inside, and then you rinse them away. So, but it's so minor effect that I don't think it's important.
Okay, there's another question.
Tell me, as the nitrates levels are decreasing, what do you do? Do you adjust the flow rate and the alcohol, the ethanol, the vodka?
Yeah, at some point we reduced the flow rate It's at the moment it's around 7 liters per hour. It went down to 3-4 liters per hour. We didn't touch the set points or anything, but then the nitrate level started to increase a bit, so it was slowly set back to. If you make a fast changes, then you have problems. The next few days or weeks, it gets a bit unstable because the bacteria, they might just die and come out. You have lots of foam coming, at least in our reactor in sea life, if you make changes. But in this case, we didn't see any foam production. So.
Okay. Yeah. Last question at the back.
I've made some tests with the same type of reactor as a fluidized bed filter with a nitrification reactor. And we saw that if the bacteria mass grow up in those reactors, the sun goes out of the system. Did you make the same?
Do you mean what kind of bacteria lives in this? Or?
We do not take it as a denitrification system.
Yeah.
We test it as a nitrification system.
Yeah.
And when the bacteria mass grow up, then the sand cones become bigger and bigger and go out of the system.
Okay, yeah.
So maybe all of the sand from time to time goes out overnight.
Okay, this doesn't do that. There's fairly high biomass, yes, but I don't know why it doesn't start to float. Well, of course, some particles may travel through the pump, and that's how they get cleaned. But most of the cleaning happens when these particles are shearing against each other. And we use oolitic sand, not coral sand. There's a big difference in that as well. The oolitic sand is easier to fluidize. If you take a bucket with coral sand and it's wet and you put the bucket on its side, the coral sand stays back there, but if you do the same with oolitic sand, it pours out nicely. So, but it's self-cleaning, and yeah, definitely bacteria escape. I've seen laboratory tests of what bacteria lives in our reactor in sea life. It's a huge list of things that live there. I will show it to you someday, but that's a very interesting subject, but there's a lot of different bacteria in these reactors.
Okay. Thanks a lot, Markus.